So last class we looked at various ways of reducing power, and we basically ended the class, kind of looking at how voltage could be reduced to reduce power and also reduce the energy consumption per operation. Today we will basically carry that forward and look at techniques for dynamically adjusting the voltage while the chip is in operation. It's called DVS, dynamic voltage scaling. So just to review again, because energy, power and performance are tied together, we know that voltage reduces, the switching energy reduces, power reduces, leakage power reduces. But also as we reduce the voltage, the delay increases, and usually most of the designs, as we said, are done in a synchronous fashion. So we have to make sure that the delay, it doesn't affect the correct functioning of the circuit. Now what determines the correct functioning of the circuit from a timing perspective? We know that in the synchronous design you have pipe stages, right? So here we focus in on a pipe stage where you have flip-flops in the beginning and the end of the pipe stage. So for example, this could be an adder with, maybe it's a 64-bit adder, it has two 64-bit inputs and one 65, 66-bit output. So there are a number of flops here. So you give the flop, you give the data, and at the beginning, at the rising edge of the clock, the data is transferred to the input of this pipe stage. The data flows through, and then by the end of the clock period, the data is ready to be captured by the flop F2, the set of flops F2, which then feeds it to the next pipe stage. So this is basically how pipelining works here. You have one full cycle in which to do your operation. Now when you look at that, sorry, the fonts here are messed up. Basically when you look at this, what happens is that at the clock edge, the data is transferred from the input to the output. It takes a while for the data to settle down, Q1. Okay, so this is called T propagation from clock to Q. TPCQ is the delay of propagating the data from the clock rising edge to the output, where it is stable and ready, and this can start working on this data. And this data flows through, and there is a propagation delay for this data to flow through and then become and appear as in D2. So after this delay of TPD, D2 stabilizes to the correct value. If it's an adder, D2 essentially has the sum of the two inputs, and it is ready to be captured by the next flop. Now the next flop, for it to capture the data properly, the data has to come and be available, be stable for some small amount of time before the clock edge happens. That is called the setup time. Okay, so at least a setup time before the clock edge happens, you have to basically be able to, the data has to come in and be ready. So this is like, when you are entering these elevators, and the elevator door automatically closes. Okay, so you want to make sure all your body parts are inside before the door closes. Okay, so it's kind of like that. You want to make sure the data is all properly inside, and then the clock edge happens and captures the data. So that margin is called T setup. If you come before T setup, you are captured properly, but if you come within the T setup, it might not capture it properly. So that means the sum of TPCQ plus TPD plus T setup has to be less than the clock period, because this is the time you have from the launching edge to the capture edge, clock period of TC. Whatever you have to do should be done within that TC. So this is the timing constraint. There is an additional term here, T-skew. We'll discuss that when we discuss this in more detail. But this is supposed to be plus here, so there is some font problem here. maybe it is plus in Chinese, perhaps. I don't know. Anyway, so now clearly as you reduce the supply voltage, what happens is that all these delay terms reduce. Probably some of you might have already found this as part of the exercise which you are supposed to have be submitting today, that you find that as you reduce the supply voltage, the delay increases. So, which means the clock period with which you are running the chip, as you reduce the supply voltage, should also be adjusted accordingly. If you keep the same fixed clock period which you use for a higher voltage and you make the chip run at a lower voltage, it will fail because this timing will be violated, right? So for every clock period there is a minimum voltage at which it will run properly. Below that voltage the chip will fail because it will violate the timing margin. Above the voltage should be okay. It will just come fast and it will remain, everything will come and settle. You see there is so much margin here. You are being inefficient with power consumption because you are running it at much higher voltage than what it needed to run, but it will run correctly. So can you be greedy? Can you make it run at the voltage where you just meet timing? That is the lowest voltage for you to run, which will be the most energy and power efficient. If you have to reduce the voltage some more, it will fail. If you increase the voltage, it works fine, but you are just wasting power. So being able to automatically adjust the voltage where you are just meeting timing with some margin, small amount of margin, will be the most power efficient, energy efficient point to run. Okay, so that is what dynamic voltage scaling tries to do. It tries to hunt and adjust the voltage such that it will be at the most power efficient point. There is also a concept of hold time. That means when the data comes, before this captures the data, but during the time it's capturing, you want to hold the data. If you change the data before it is captured, you will basically not get the data. It's like the lift is closing, you come out of the lift. Okay, so the lift, now there is no one in the lift, so you are not in the lift. So it's the same thing. You don't want the data to change before the before that. So that is hold time. That doesn't come in the critical path, but it is important for making sure everything runs properly. But it doesn't affect the critical part timing. It doesn't determine the speed at which the chip runs. We'll discuss that more when we talk about timing and clocking and so on later. So what we saw is that the frequency as a function of voltage has a shape somewhat like this. As you increase the voltage, frequency goes up, and you can imagine there is a certain saturation. There is a certain max frequency you will achieve, and there can be quite a bit of play available here. That means you can run from a gigahertz down to megahertz, based on what voltage you run. Okay. Of course, you have to make sure your circuits will run at slow speeds also. Sometimes you can design circuits which don't run at slow speeds. Of course, they will not run at very high speeds for natural reason, but also it can happen that they don't run when you run it slowly. So we will see some examples of circuits. Essentially, they have got to do with leakage. The circuits are relying on information being kept dynamically. Okay, and then and they get consumed quickly. But if you are running so slowly, the information gets consumed only at a slow rate, and it can leak away. So if you use such circuits which use dynamic circuits, there is also a lower bound. You can't run the things too slow. Now we saw that this frequency versus the voltage curve, there is no single curve which defines that frequency versus voltage. For a particular design, there is a family of curves based on the process condition, because the threshold voltages, there is no fixed threshold voltage, there is a spread in threshold voltage. The operating supply voltage could be a little different. You are applying 1.2 volts to the chip. Another chip also is thinking 1.2, but it might be a little bit off, 1.25, 1.15. There is always a tolerance given. Similarly, temperature of operation could be different. So you see there is a spread in the frequency versus voltage. So if someone were to ask you, okay, for this frequency, what is the voltage at which I need to run? If you were to believe only one curve, you can say this is the particular voltage. You look at that frequency, you look at the frequency to voltage curve, and you say that is the voltage I want to run. But there is a spread in that curve. So if you want to be conservative for a given frequency, you want to run it at a voltage where no matter what the condition is, the chip will run at that voltage. So you have to what is called margin. You have to give margining. It's called margining. You have to put in a margin to allow for these process voltage temperature variation. Okay, and this margin can be quite a bit, and this concept of so there are two concepts here. One is dynamic voltage scaling, where if you are running at a lower frequency, you adjust the voltage to be lower, to be just enough to run it at that frequency. So if I know I'm going to run it at this frequency, use this voltage. In addition, you also have to put a margin, because different chips from the same class might have different F2V characteristics. We can call this F2V characteristic. It could be a little different, so you have to put in a margin for that, so that no matter what chip from that class is being used at that frequency and for that voltage, it will work. Now that concept of adaptive voltage scaling also tries to take away that margin. Instead of always using a fixed margin, if you knew for sure for your chip what is the F2V curve, then you can appropriately set up the voltage optimized for that, instead of always using this worst curve. So that is what adaptive voltage scaling does. It tries to take out even that margin of process and voltage and temperature. Now we'll just go a little bit more into this process voltage temperature variations, just to kind of get a sense for why that happens and how to deal with it. So you have these, essentially we are talking of variations in the transistor's characteristics. The most important parameter is the threshold voltage, right? Because the gate overdrive of the threshold determines the drive current, which determines the speed, and the threshold voltage also determines the leakage when it's off. So the threshold is the most important parameter, and the threshold voltage itself depends on many other parameters. It's a function of the doping concentration, it's a function of the channel length due to short channel, narrow channel, reverse short channel effects, it's a function of the channel widths, function of the oxide thickness, the materials, etc., etc. And so there is always some variation. So that is why threshold voltage is really the proper way of looking at it. It's a random variable which has a certain mean and a certain spread. Now what happens is that if you look at these variations which affect the chip, you can classify them as variations which happen at a very slow time scale. So this is what this is saying. In this dimension we are looking at the time scales of change of these variables. Static means you get the value of the variable, you don't know what it is, there is a randomness, but it's fixed. During manufacturing you get something, and once it's there, it's there. Whereas dynamic is even during the lifetime or operation of the chip, it can change. Okay. Now what is interesting is that, so you would think that threshold voltage, once you make it, it's fixed, because doping concentration, channel length, etc., etc., all of them are fixed. So you get some fixed value. So it should not, it is random, but it is fixed. It's determined during manufacturing. But it turns out that, so the threshold voltage varies from chip to chip. When I say threshold voltage, which threshold voltage I am saying, right? I am using, because every transistor has its own threshold voltage. So if you take the same transistor in another chip, because you are taking the design and you are stamping it, right? The same thing you are stamping. The same transistor you looked in another chip, that transistor's threshold voltage will be a little different from the transistor, the voltage in another design. Okay, so chip to chip there is variation. That is called inter-die. That means across die is a chip. Across chips there is a variation for the same transistor. Now within the same chip you have many transistors. Same AND gate you are using multiple times. The threshold voltage, even though you have used the same AND gate, you have just taken a copy of it and put it, still the threshold voltages could be a little different. That is called intra-die variations. Within the die itself there is variation, across dies there is variation.
So even on the same process?
Same process, same chip, one chip you take, same AND gate, you made another copy somewhere else, it will have a slightly different characteristic.
You are manufacturing the chip and fabricated AND gates will be fabricated. At a time some temp or hundreds of AND gates will be fabricated.
Intra-die, absolutely. So the question is, even though the gates are being fabricated at the same time, in the same process, in the same chip, will there be variation? Yes, answer is there will be variation, because if you go back and look at the threshold voltage, what determines the threshold voltage? There are factors like the channel length, the doping concentration, etc. Now you go back and think about the doping concentration. Okay, now we are talking of channels which are very small, because as you're scaling down, you can have maybe 1,000 atoms, dopant atoms in the channel, maybe less. Physically, where are the dopant atoms? If I take two transistors, maybe in one transistor there is a certain distribution of the dopant atoms in a 3D space. In the second, it might be a little different, because the dopant atoms are kind of coming in from the top. They are bouncing off and falling in. Maybe they are entering through different trajectories and get embedded. You don't know. The number which will get embedded also you don't know. Okay. Similarly, the channel length. The channel length when the transistor is manufactured is basically by etching the gate. You deposit a gate material and then you etch the gate material. The etching is a chemical process. So the gate, when the geometries are defined, you will not get a perfect straight line with a ruler. If you really zoom in, you will find a lot of jagged edges. It's a chemical process, it's fighting and it's taking out. So you will have jagged edges. So again you see that the notion of a gate length itself becomes, a gate length itself is a random variable. It has a certain variation. So all this cause variations in the transistors, even though you supposedly identical transistors. So what that means is, if you really want, as a corollary, if you want very good matching, you want to make sure you not only replicate the sizes, you replicate the layout, as well as you replicate the neighborhood. Because the neighborhood of the transistor affects, for example, the dopant. It bounces off perhaps things and falls in. Light, which sets up the pattern, diffracts. So everything has to be made identical if you want really good matching. Okay, which is required for analog applications, not for digital. You also have changes when you make a chip. Chip runs at certain speed now, but after 5 years it will run at a slightly different speed. It ages, and you have some, maybe the oxide slowly starts degrading, maybe certain charges get buried because you are operating at high voltages. So slowly you have some charges embedded in the oxide. Whenever you have a charge in the oxide in the channel, above the channel, it changes the threshold voltage. The oxide, the charge could be mobile charges which slowly move with time. Positive charges embedded. Over time, if you keep on applying a negative gate voltage for a PMOS, it will slowly start pulling that charge, and it will cause a shift in the threshold and cause slowly threshold to change with time. So when you design the chip upfront, if you know, especially if you design a chip for a cell phone, probably you don't have to worry about the life being more than maybe a few years, 2-3 years. Right? People keep changing cell phones. But if you design a chip for a car, 15 years, 20 years, it has to be there, right? Planes, those kind of things. So there it really becomes important that you think about how will the thing work after 15 years. So that has to be factored in when you do your analysis. You have to put in margins for all of that. Pardon? Mainly the threshold voltage basically changes because of because of some changes in the oxide, above the gate oxide, above the channel. You can also have slow changing. VDE maybe changes slowly. Okay, ambient temperature, of course, you are operating here in the room, it starts heating up, things, when you go out, it's cooler, so on. And again, you can have global changes and local changes. Global changes are changes which affect the whole chip. Local changes are changes which affect portions of the chip. Okay, so we said intra-die process variation. Local, the voltage is not uniform for all the gate. Every gate will see a slightly different supply value depending on where it is in the power grid. Temperature could be different across the chip, and you can have very fast changes. Okay, these are changes where the clock period itself, TC itself changes. Cycle to cycle there is a change in TC. That is called jitter. Because whatever is generating the clock is a noisy source. When noise comes in, it can affect the cycle. So those are very fast changes. How do you deal with that? You basically put margins for that, because it's very difficult to track those changes. When changes are slow, you can think of circuitry which will track it, compensate for it. If it's a static change, if you can measure once, you can compensate for it, for a static distance. If it is a slowly time varying change, you can have some circuitry which measures and keeps adjusting. As long as the circuitry which is measuring and adjusting has a speed much faster than the change at rate of change, right? So that is basic control system stuff. But when for fast changing, what do? You have to margin it. You have to say, look, I'll assume the worst case period degradation and make sure my circuitry will meet that worst case period. Right? That's what is basically done. And these changes could be global. That means because the clock is coming from a global source, so the period change is uniformly seen by everyone. Or it could be local because you have this clock in a local region which has coupling coming from another signal, which for us that period it changes locally for that small group. So you have all these changes, and really you see the engineering design is in some sense to engineer something and make it work reliably, robustly. All these had to be accounted for, and usually they are accounted for by a simple way of margining. You say, look, I don't know what these, I'm going to be conservative. I'll design my chip to run, you want a 1 gigahertz chip, I'll design it to run at 1.2 gigahertz. You want it to run at 1 volt, you say I'll make sure it will run at 1.2 gigahertz at 0.9 volts because there's too many things going on, I don't know. So that is kind of the margining which used to be done. It's still done in some places, some cases, but problem is you end up putting in so much margin that you can end up designing a chip which is not very competitive. Well, maybe you didn't need to put that much margin. If you had more visibility on these mechanisms, you could do something smart. So that has been basically the mantra which has emerged over the last 4-5 years to try to have smarter designs which can reduce the amount of margining you put in your designs. So just to again explain this concept of global and local variations, see, these chips are made in wafers. The wafers are circular silicon dish type, it's like a flat surface, very thin, and on this you make these chips and you dice it up, right? So each of this diamond shape is a chip. As we said, within a chip you can have variation. Chip to chip things could be a little different, and you will have a bunch of wafers processed in a shot. So that is called a lot. You do it once and then maybe after a month you do again another lot. So there could be variations across the lots because the equipment you have used to put in this chemicals, etc. Maybe there's a small change and maybe chips come out a little differently, right? So that is why you have these variations, and then again within that same chip you could have little variations because, for example, a lot of this processing, what happens is that there is the whole wafer is not, when you expose to do patterning, pieces of the wafer are exposed and then it steps and so on. So exposed to light. So maybe around the edges things may be a little different. So there are a lot of physical mechanisms which cause changes in the way the transistors actually come out. And you can have changes which are correlated, changes which are random, so on. Like if you have, maybe the temperature setting was a little different for that particular wafer. Okay, then there is a correlation of the variation due to that in all the transistors of all the chips in that wafer. But any variations due to this random bouncing of things or diffraction of light and so on is very random. There is no correlation. Right? So you can have correlated and uncorrelated, and the way you deal with this will be different. And we already talked about aging related effects. If you take a chip and you look at the supply voltage of the chip across the chip, so this is essentially mapping the supply voltage. Red means the supply voltage has dipped quite a bit. Blue means it is what it is supposed to be. So based on the value of the supply, VDD to the gate could be a little different based on where the gate is, and can change dynamically pretty fast. Temperature, right? Temperature could be non-uniform across the chip. Some places which are very active, it will become hot. Places which are not active, it will become cold. And as we discussed in one of the earlier lectures, temperature affects mobility and the threshold voltage, and so the speed gets affected by temperature. Of course, also the leakage gets affected by temperature. And then we already discussed these fast fluctuations due to clock. L di by dt is the, L is the inductance, di by dt is the rate of change of current. So when you have current coming in and going out through the pins, IO pins of the chip, the pins have inductance. Whenever there is a current change across the inductor, you have a voltage drop across the inductor. Whenever you have a voltage drop from the external battery, you lose some voltage to the voltage drop in the pins, so that affects the voltage in the chip, and so the speed gets affected. So IR drop is a drop in the resistance of the wires in the power supply, in the pins, etc. There is some resistance. It's different from LDI by dt. LDI by dt is related to fast changes. IR is just average current is there, or even any current times resistance, there is a drop. Capacitive coupling we have seen, clock tree jitter. You have a clock, it's distributed, and the distribution network essentially consists of inverters and buffers. If the supply voltage to that inverter changes because of LDI by dt IR, the delay of that inverter changes. So the delay of the clock edge coming at the flop will also change, which will lead to jitter. So all these cause you to have the spread, and you would basically, at least you will have spreads because of static variations due to process changes and dynamic variations. And when you design a chip and you say for this frequency I want this voltage, you give margins for that and you say this is the voltage I want to account for all these changes. Now the adaptive voltage scaling, what it does is, at least changes which are static, can I figure it out, or changes which are slowly varying, like temperature slowly changes, can I take that out from the margining and try to use a lower voltage as required for that. Remove that extra margin I put in very conservatively, so that you can reduce the power consumption. That is called adaptive voltage scaling. So how do you do this in a dynamic way? Now we saw in the last class that one approach to do this is to actually, really you need to capture this frequency to voltage curve somehow. One way is to capture this curve in the form of a table. Okay, based on simulations, you can identify, you say there are 3-4 different frequencies I want to run, and for those frequencies you say, okay, these are the 4 voltages, and you set it up in a table and you do it. Now what you have done is, at least you have implemented dynamic voltage scaling, where at least based on frequency you are adjusting the voltage, but you have still provided the margin, you have left the margin on the table, because you are not doing anything about the silicon. Maybe the silicon is much better, maybe the curve is here, not here, right? So you are not doing anything there. You can say, look, I can even take care of that. Basically what I will do is I will put some little ring oscillators, as we discussed in the last class. Ring oscillators are essentially chain of inverters, odd number of inverters, where the output is again connected back to the input, so it will oscillate. So you will measure the frequency of the oscillation, and you will know, you will get a sense for which curve are you in. Are you in this curve, or are you in this curve, or some intermediate curve? And based on that you use the right value in the table. Maybe you have multiple tables, and then use the right table for that particular chip. You figure out which curve you are in and use the table for that. You can also do ring oscillators which are spread out. Maybe here we saw how you have 4 different regions, right? Maybe you have separate voltages for each region, multiple VDD within the same chip, and each one you characterize, and then each one you have its own customized voltage. So that frequency versus voltage curve, right? Is there a way to somehow get it right from the chip itself? Okay, ring oscillator is one approach. Is there a way to, really what you want is to have a way of figuring out what is the critical path in the chip, because that tells you what voltage you need to run. That critical path has to run at that particular frequency. It has to have that particular delay target. So you adjust the voltage to be low enough such that the critical path just works at that voltage, and that is the best voltage to use. So really this is the overall system, right? You have a controller, you have a way of measuring the critical path and keep adjusting the voltage till the critical path just works. Okay, or maybe, right? So now the question is, how do you measure the critical path delay? So people right now largely do this by having a model of the critical path on the side, and then measure the model, because the critical path in the actual chip, so many pipe stages, it could be very complex. And how do you do a measurement right there in the chip out there? It's not very easy. So you have a model of the critical path. So how do you make the model of the critical path? Now this is an idea which was proposed a while back, more than 23 years, more than 20 years ago, and only now these kinds of things have become quite popular. Right? So usually it takes about at least 10 years for concept in a research to get accepted and implemented in a commercial setting. What you want from the model is the model should be faithful to the actual critical path. The actual critical path has a certain frequency to voltage characteristic, that is the DUT, device under test speed. The critical path should be such that it follows this, but it's a little conservative, just to be on the safe. You're still given a little margin, so that what you do is you measure for that frequency, you see where the critical path, what voltage is required for the critical path to work, and then you use that voltage for the rest of the chip. Now, I mean, if you just think about it, why this margin is required? Because how do you, I mean, just think about the algorithm for doing this. Suppose you want to hunt for the voltage. Maybe you start with a high voltage. You start reducing the voltage till a point where something fails. Then you say, okay, you reduce too much and you back off. Right? So that is why you need the critical path model to have a little more margin, because even though the critical path model failed, the actual thing would still work because it has failed by a small amount, but the actual thing is still working. And then you use that voltage for the actual circuit. Correct. So absolutely right. So this critical path, the F versus V, also depends on temperature. So the critical path model has to be able to sample the temperature also. So hopefully if it is in a region where all of them are at the same temperature, the critical path model also has the same temperature as the actual circuit. So one way of measuring the critical path is simple ring oscillator. You set up a ring oscillator, you put in the right number of stages such that the period of the ring oscillator has the same delay as that of your critical path. And then, you can actually use some circuitry to use that and adjust it. Maybe some of this stuff might not make sense right now, but basically this kind of thing using ring oscillators is very common. You put it in because you want to, even from a point of view of metrology, process metrology, you want to understand how good the process is. Very small, very low area head, very low power, etc., etc. Okay, and in this ring oscillator you put in margins for all these other variations which are very hard to deal with. Right? You put margins, power supply fluctuations. Okay, you say power supply is plus minus 5%. I'm going to assume minus 5% and put that margin. Things like that. That's how basically you do and put margins. Aging degradation. You say, okay, over 20 years, I expect my chip speed to degrade by 5%. So again, you put in 5% margin in your design. So like that, you put in margins for things which you cannot deal with in an adaptive way. Now the thing is, if you take a critical path, the critical path will have gates as well as wires. Okay, so if you want a good model of a critical path, remember when I say model here, the model is also in silicon. It is not the mathematical model which is there only during design time. It is a small piece of circuitry which is modeling some other bigger piece of circuitry. Some characteristic of the bigger piece of circuitry is being modeled by the smaller piece of circuitry. The smaller circuitry you have made because it's easy to measure it. The bigger, measuring the critical path delay is very difficult in the actual circuitry because it's you don't know where all the, it's like it's all kind of distributed. Here it's a small piece of circuitry you can put next to the controller in a place where you can measure. So what people do is that you can create a critical path model with gates, maybe mix of gates. That is what these guys, Japanese guys, have done. They have a bunch of gates. They can configure how many gates are the logic gates are there. This is wiring. So what they do is they have a long piece of wire. They tap off from different portions of the wire. So you can adjust what is the wire length you want to put into the model. You can adjust the number of gates you want to put into the model. You can adjust the number of buffers you want to put into the model, and so on. So this is how they construct the model. In silicon, they'll instantiate this piece of circuitry which they can configure to get and configure the model. Now this model which they configure is done once per design. If they have a MPEG decoder, they take the same IP, they put it in, but then they say, okay, this is the settings for the mux. They don't change it chip to chip. Yeah, that becomes too, every chip, if you go and figure out the setting, it is more intense process. But an MPEG chip will have, a processor chip will have a different setting and so on. So class of chips. The design is, you do the design once, you instantiate it, but you just configure the setting differently for different classes of chips. And then what you do is you measure the delay out here. Now this whole thing you can configure as a ring oscillator. You can take it and put it back. As long as there is an inversion, it will keep on oscillating, and you measure the period or a frequency. That is one way of making the measurement. Now when you say measure the period or frequency, you want to do it in the chip, not put it in a scope and see. It has to be all built in inside, automated, right? How do you do that? How do you do the period measurement? So it can be a little tricky, whereas delay measurement is relatively simpler. So that's what they do. So what they do is they have this chain of gates and wire and so on. You excite it with a pulse. After some delay it comes. Then you measure the delay. We'll see next how you measure this delay. Okay. So what you do is the following, right?
Stage can be checked instead of chaining all the stages. But those individual changes be checked and the performance be evaluated.
Okay, so the question is, can we not measure the delay of each of the individual stages and then from there estimate the performance? So I want to clarify one thing. See, this is just an additional piece of circuitry which is put in the chip to mimic the actual critical path. Okay, so this by itself has no significance from the point of view of actual work being done by the chip. It's just out there to help measure the actual critical path. So the idea of this piece of circuitry is that you set up the right number of stages for the wiring and gate and so on, so that you mimic the actual critical path. The actual critical path will have a certain mix of gates, certain amount of wiring. Of course, you cannot put all the gates here, because the actual critical path you might be using all kinds of logic gates. You can have thousands of logic gates in a library. You have to be a little practical. You can't put all possible gates here. It will just blow up this, it won't be. So this is a compromise. You say, look, I'm just going to put a bunch of NAND gates, some wire and some inverters. And I'll allow some selection of how many gates, NAND gates I want to put, what length of wire I want to put in by setting the muxes. So that is why it's called a model. It is modeling or mimicking the characteristic of the actual critical path. Of course, it will not be perfectly able to model, because the actual critical path might have all kinds of gates. But the idea is, hopefully you will do close enough. You will have to live with some margin, but that margin is hopefully small, so that by measuring this and adjusting the voltage says that this meets this delay you want. Suppose you have a delay of 1 gigahertz, frequency of 1 gigahertz target, which means 1 nanosecond period. If you say, look, I'll adjust the voltage so that this from input to output is 1 nanosecond, and that voltage ensures that this is a 1 nanosecond, then with high confidence I should be able to say that same voltage, if I apply to the actual chip, it will also run at 1 gigahertz. That is the intent out here. So there is no reason to be measuring these individual groups, because the whole thing itself as a group, the whole chain is supposed to model the delay of the critical path.
Sir, how to measure the actual critical path?
So the question is how to measure the actual critical path. What happens with the actual critical path in silicon? Of course, in simulation you can measure, because you can always, in simulation you have access to all the nodes, right? In simulation or during design time analysis, static timing check and so on, you have access to all nodes and you can get it. But in silicon, how do you measure? To measure, you need to be able to access the input and output, and you need to be able to access the waveforms. Input waveform, how do you measure delay? Delay is 50% to 50%. So you need to be able to access that. In some sense, you trigger from this. At the input, you launch an edge, and the output, you capture the edge, and you look at the delay between the two. That is very, very difficult to do in silicon for an arbitrary critical path, because all the nodes are so embedded. How do you access that physically, right? It's very difficult. So, but the way to kind of infer So that is also an important problem, right? I mean, one way of inferring is that what is called, when you test the chip at a particular voltage, you put a voltage and you run your test. You see everything is okay. Then you increase the frequency, run it again. Increase the frequency till you reach a point where it fails. Then you know for that voltage, that is the frequency at which it runs. So like that you can get that frequency to voltage curve of the chip. That is called the Schmoo plot. You get that. But you don't know within the chip which portion has failed. You know it has failed at that frequency, but you don't know which portion. To get that information, you need to have additional circuitry inside the chip to be able to get that. And that requires additional circuitry to be put in. Which, yeah. Correct. So you can have what is called a Schmoo test, where you run the test just as I described. You run it and you see at what voltage it fails for that frequency, or for that voltage what frequency it fails. So that way you can, and if you are testing for multiple different voltage points, you have to set it up, and then you can get that Schmoo plot. Now, absolutely. So the question is, how is this testing done? That is something which we'll cover later in the course. There is a built-in self-test. You have to put in extra infrastructure in the chip to allow you to do this testing. You'll also have testers, which are big machines, very expensive machines, in which you put in the chip and the testing is done. So there is some help from within the chip, and that it works together with the tester to actually help finish the testing. The tester time is very expensive, so you want to do your testing with as little time as possible, so that quickly the chip can come out and you can say, is it good or is it bad?
So say so we replicate the same chip and get a better visual model.
So the question is, once the design is done, you will have a critical path. Why not somehow mimic that critical path and use that as a model, right? That is basically the question. I think that's a very valid, and you can do that also. The problem is that if you change the design, okay, if you change maybe the same design before tape out, you realize there is some issue. You have to make some change. The critical path could change very well. So till the last minute, you don't know exactly which is the critical path. So even the critical path model will have to be adapted like that. Secondly, the critical path itself could be very complex in the sense of, the actual path might have a lot of fan out and so on. So it may not be that easy to replicate the same thing. See, because the critical path is spatially, there is a spatial structure to the critical path, because the signals are going and wire is spreading out and so on. Replicating the same thing might just take too much area, and you will not be able to anyway properly replicate it because of that. So instead of doing that, you just have this kind of a approach where what you are saying is, I don't care exactly what the critical path is, but whatever the critical path is, I am confident that by setting the muxes here, I will be able to mimic it reasonably. So that is the idea. And then now, once you have this approach, the model is done once. Today you do MPEG chip, tomorrow you do a software defined radio, you do something else. I don't keep changing this again. It's done. I just stamp it down. It's just a software reconfiguration problem. Okay. You want to push as much as possible to software. Okay, so that is very important in general. So how do we make the delay measurement? Okay, so this is something which is kind of interesting. You basically, they are calling it the delay synthesizer. It's another name. I can call it a critical path model. It's also a delay synthesizer. That means it's synthesizing the delay of the critical path. That's why they're calling it a delay synthesizer. So what you have to do is you launch the pulse, and then when the pulse comes out, you have to measure 50% to 50% delay. If you were to do it in simulation, or this is what you would do, right? You will see the pulse which is going in. You see the pulse, the edge which is coming out, not pulse. and then you measure 50% to 50% in the somehow in the oscilloscope or in the graphical tool, whatever. But how do you do it in hardware? What they do is the following: they launch the pulse using one of the edges of the clock. Just ignore some of these other things here. It's not just the idea is the following: the rising edge of the clock, you launch the pulse. Okay, the pulse comes, the edge, sorry, rising edge of the clock, you launch an edge out here. After some delay, the edge comes here. And this edge propagates through this chain of buffers. You take, at the output out here, you have flops. And the next edge of the clock, you trigger these flops to capture the state of the nodes here. So when you capture it, you will get, say, 1, 1, 1, 0, 0, 0. Let us say you had a signal here which was going from 1 to 0. Okay. Oh, sorry, 0 to 1. So what that means is that when you, at the next edge, when you get this 1, 1, 1, 0, what you can infer is that this edge is between here and here. It's somewhere here. Because 0 to 1, this has gone to 1 because you captured a 1. This has also reached 1, you have captured a 1. This has also reached 1, because you have captured a 1. This, you have captured a 0. That means this rising edge is somewhere in between those two. Okay. So you have an idea for where the edge is, how fast the edge has propagated. Right? It's like, you have a 100-meter race, you say start. Okay, then exactly after 10 seconds, you take a picture and take a snapshot. The person would have reached, if it was Usain Bolt, he would have his arms up in the sky and celebrating. If it was one of us, we would be maybe in 50-meter mark, right? So it will be kind of like that. The picture, you're taking a snapshot and analyzing where the person is in the spatial domain, you kind of see whether he has reached the 100-meter mark or he has not reached the 100-meter mark. Here what we are saying is, what you want to do is the 100-meter mark, you want to make sure the person comfortably reaches, and he has gone beyond that a little bit more, maybe 10 meters. So you say what you want to do is, you always want to ensure when the delay of this is such that this delay plus maybe you kind of say that, look, I want to make sure that I have reached at least 2 additional buffers. That is up to you as a designer. You can say, or 3 additional buffers. I will adjust my supply voltage such that when I make a delay measurement, my edge has propagated beyond this at least 3 buffers. It could be more, which is okay. But if it's 2 more, then that means my voltage is too high. I keep reducing the voltage such that I reach my delay of the synthesizer plus 3 buffers I've reached. Right? So that is basically how you set up the control loop. And this additional thing is just encoding to see where it is and so on, and then it gives it to a state machine which will then adjust the supply voltage and so on. But the key of measuring the delay is done like this. So we are not making absolute delay measurements. If you see out here, I am not making, this is the so many nanosecond delay. All I am saying is my delay is such that in one clock period I go past the delay synthesizer plus a few additional buffers. How many buffers is up to the designer. It's like a margin I'm putting in, just to be on the safe side. That is the voltage to which I convert. Okay, so there are other ways of doing this. So in this approach, this is by IBM. What they do is, they have these gates. See, now they are putting adder here. See, this is again a model of the critical path. They have actually put an adder. They have put NAND 4 gates, not 3 gates. They have wires, they have pass gates, etc. And again, the idea is the same. You launch it, and then they have this configuration capability. Which one do they choose? Do they choose adders? Maybe different designs have different mixes. If it's a filter type design, it has more of multiply accumulates and so on. Okay, so see, again, it's a trade-off. If you put in a complete multiply accumulate, it will have a much better mimicking of the actual multiply accumulate. But then you have so much area you have spent. So you see, there are these trade-offs. You have to be smart to use as little as area as possible. At the same time, be reasonably close to what you're making. So, so basically, you come in here and then you have this edge detect. It is the same as this, they call it the delay line gauge. Okay, so this concept is used a lot nowadays, so it's very useful to learn this concept of measuring delay. They are used in what are called TDCs, time to digital converters, where you measure time, and you cannot measure it basically like this, because what you're doing is you're measuring it using your measuring unit is this buffer here. In this case, it's this buffer, that is 1 unit of measurement. Here it is an inverter. So what they do here is, instead of using a buffer, the previous work by Nakai used a buffer, which means 2 inverters. Buffer is non-inverting, whereas here they have used a simple inverter. So you see how many buffers it has crossed. So you can measure the delay in units of buffers. In this case, units of inverters. So your inverter becomes a unit for measurement of delay. So in these kinds of approaches, your unit of measurement is the delay of an inverter, and these are, if you see, maybe fan out 2 inverters, because this inverter is going to this inverter plus it's driving some load in the flop. So what is the resolution available with these techniques? Fan out, about fan out 2. Okay, so in your 16 nanometer process, maybe 4-5 picoseconds. So you can measure time very easily with this kind of technique at a resolution of few picoseconds. There are techniques which allow you to measure time at less than a gate delay also. Sub picosecond also you can do, but that is for another time. So now you have this edges here, again the same concept. The edge comes in here and then it gets captured. Okay, that is not shown here, but what it gets captured by these flops. It's like taking a snapshot. You take a snapshot and the output of the flops are essentially capturing the state of the nodes out here in the delay line gauge. And because it's alternating, they are doing this XORing. So it says that the XOR is looking for a transition. Where is the edge out here? And then after you do the XOR, you see all ones and the 0, and you see that the transition has happened at this point. So you see that edge has traveled up to that. So this is kind of what is done basically. It's just another critical path monitor, but the technique for measuring the delay is the same. Okay, a small variation of inverter versus buffer, and using this XORs to get you the transitions. So what they do is they report the delay of all these different models they have put, adder, NOR3, NAND4, passgate wire, across the supply voltages. One thing you see here is this, on the x-axis the supply voltage is just going from 0.9 to 1.2. They are just playing around in that small window. These commercial chips usually will be operating at that small window. They will not try to push it too much, because those are still uncharted territories, pushing the voltage down too much to 0.5, 0.6 subthreshold and so on. So that only research chips are happening. But as I said, another 5 years maybe you'll have more chips going down even to much lower voltages. What this graph is showing is there's quite a bit of tracking of the delay with each other. What this graph is doing is that it's showing the average bit location at the maximum frequency for all these different monitors. The monitors are essentially by setting the mux switches, and you know, the thing is that the monitors themselves, different monitors have different bit location. What does the bit location mean? It means when I have my capturing edge, how far into the delay line chain have I propagated them, how many bits. That because each bit is this is a bit, each flop is a bit. So how many bits into I have come in. So different ones have different, they come into different bit levels, and the bit positions are also a little different across the different voltages. So what is the end result of all of this, right? Let's come back to the results reported by Nakai, right? If they didn't use this critical path model and adjust the supply based on the critical path model versus doing it, what is the difference? Are they really gaining anything? Okay. Now we are talking of at a particular frequency, there is a frequency target they want to run. The voltage they want to use, if you didn't do anything, for a fast chip versus a slow chip, you will use a fixed voltage. You will use a voltage such that the slowest chip will run at that particular speed and voltage, and this they are saying is 1.55 volts. At that point it gives you 572 milliwatts. There are two curves here. The dashed line is the dynamic power, the solid line is the total power, which means it also includes the leakage power. So they are at the slow chip, they are at 572 milliwatts, and then the same voltage if they were to use for a fast chip, they'll end up burning 645 milliwatts. So there is a variation from 572 to 645 based on because of the difference in the threshold voltage, and they are using the same voltage. But suppose they turn on this critical path model and this feedback system, then what they find is that yes, at slow I still need to run at 1.55 volts. I mean that I cannot change. This chip you have to put 1.55 for the slow process, and it will burn 572 milliwatts. But at a fast corner, you see the voltage they are using is 1.33 volts. The thresholds are smaller, and the system is able to dial down the voltage, and so they are able to save dynamic as well as total power. Instead of 645 milliwatts, it comes to 458 milliwatts. So they are able to save power. So that's basically what they are saying, is that across process corners they are able to adjust the voltage such that you are able to optimize and use as little power as required. This is how they are adapting to the process conditions. So that's why it's called adaptive voltage scaling. This is at a constant frequency. Exactly. This is at some fixed target frequency. You are able to adjust for the process conditions of the chip. Fast chip means it has lower threshold voltage. That's why its transistors are fast. So you can also reduce the supply voltage, because gate overdrive, you want to kind of, because threshold has come down, you can also reduce the VDD and still get the same gate overdrive. This is the overall system. Remember, last class we talked about frequency management. So they have a system where they do dynamic voltage and frequency management. So here they have something which adjusts the frequency, and then for that frequency they adjust the voltage. So you have both frequency control and voltage control. So that is why they get this DVFM, dynamic voltage and frequency management. How do they adjust the frequency? What they do is they basically look at the activity in all these blocks. Embedded DRAM controller, you look. What do you look? A controller, embedded DRAM, someone will make a request. Get me this data. So that request they'll count. Okay, all they have is counters. They'll take a window. Okay, let me monitor the activity over the next 100,000 cycles. In that 100,000 cycles, you count the number of times the DRAM gets accessed, the number of times the bus gets accessed, the number of times the ARM core gets accessed, and then you get an idea for how much activity has been there in that 100,000 cycle period. I'm just throwing the number 100,000. It could be, maybe 1,000. It could be, it depends on the system level configuration. In that window of time, you observe and count the number of times you have accessed the various resources. If the number of access is very small, you can say I don't need to run that fast. Not much is happening. If it's very large, then you know that a lot of things are happening. So based on that, you can adjust the frequency. Remember in the last class we discussed how do we adjust the frequency, how do we know what frequency to run. So this is one way of monitoring the actual activity in the chip, and then saying okay, for the next phase I am predicting that whatever happened in the past is a good model for what will happen in the future, which is a warning which you must have seen whenever, if some of you are into investing in stock market, probably they say, right, mutual funds, past performance is not a good indicator. Use at your own risk. But then what do you do, right? You have to, that's what you have. So it's kind of like that. You use the past performance to indicate whether the next time same thing is going to happen. And so you basically adjust the frequency. Now once you have adjusted the frequency, you hunt down the voltage using the critical path model such that you use a voltage which is just optimal for that frequency. So both frequency and voltage keep getting adjusted in this continuous fashion. Okay, so the overall system basically has This chip has all of this. They have shown this in a very big way, but actual area for this will be small. Most of the area will be all this stuff. They also have a voltage DC-DC converter, which from the, there will be a supply source here. From there, the DC-DC converter generates the voltage based on what the controller tells it. The controller will tell me, okay, reduce the voltage, it will go and reduce it, and then the new voltage will come. And then you see out here, the PLL, which is the clock source, clock distribution, etc., are kept outside this voltage. They are running at a fixed voltage. There are certain things which have to run at a fixed voltage, the IOs, the clock generator, etc. But then a lot of the things can have adjustable voltage. So, you can look up some of these papers, Nakai and then the other one, just 2 papers, not much. So you just kind of browse through them. And hopefully with this, now you have a picture for how everything works. This is one example, but it's a nice example that everything is brought together in the same chip. So you will get an idea for how this whole thing works together.